say that P is locally called locally finite, if this number is always finite, if every compact E and every large positive and E is finite. That means this is equivalent to saying that there does not exist a sequence Ci of circles in P such that Ci converges to C in C. The way you want to understand, you don't have a sequence of circles converging to you don't want a sequence of circles of radius converging to R towards some particular circle of radius R. So you don't want infinitely many circles of radius strictly bigger than something lying inside some compact E. So that's what it is. Okay. For example, if interiors of C in P are disjoint, then P is locally finite. So once given this, I define a subgroup gamma. Okay, so after this
don't you want the radius to be large? I mean, to count the large one?
Radius to be?
At present time.
Curvature less than T. Okay. So curvature less than T, so radius of C less than 1. Small, no, greater than 1. I'm sorry. Go to stop me. Nonsense. Okay, so before I go further, I need to introduce some rule. So we say that Mobius transformations on C, okay, that is look at the group G equal to P SL to C, and G acting on complex number Z. So we have acting on complex number Z is by definition. And this extends to Z. Okay. So if it's infinite, you have appropriately, then ABCD are complex number, determinant is 1. So this is the action of Mobius transformation. And so G acts on C hat, and in particular on C. So you define gamma equal to those, and so this action takes circles to circles. So if G is to C, then G times a circle is so it preserves circles. So you define gamma is equal to those gamma in as in G, which is PSL to C, such that gamma preserves this collection of circles. So in general, if you just take arbitrary collection of circles, this gamma will be trivial or just finite or something. But I want gamma to be big, so I'm going to assume that gamma has finitely many orbits on it. So essentially it is almost transitive. Okay? It's only finitely many orbits on it. So this is a very restrictive condition, and under this condition I want to estimate somehow this number as t goes to infinity. So I am going to assume P is infinite collection, and so let me give some examples of this situation. standard example is Apollonian circle packing. So of course, we take three tangent circles, and then you take a circle which is tangent to all three of them. Okay. So C1, C2, C3, C4, mutually tangent circles. Okay. And now what you do is that you start with this original configuration and you fill up the things by given any three circles. You fill up the interior by a new circle. And then keep repeating this process. So you do it in suitable order. So you have an infinite collection of circles. Okay. So I'm not writing the details, but this way you can get infinite collection of circles, and this is called equivalent circle packing. Okay. And it's clear that this is locally finite packing because the interiors of all these circles are disjoint. So it is going to force you a locally finite packing because every time the radius of circle will become smaller and smaller. So they are not given any small positive number. There are only finitely many circles of radius bigger than this configuration. So it is locally finite. Now, how about symmetry? So symmetry is very interesting. What you do is that for every I between in 1, 2, 3, 4, let AI in the circle passing through tangent points of Cj, where j is not equal to I. Okay, so Cj is in 1, 2, 3, and 4, and you just so you originally we had 4 circles. And suppose I call it C1, C2, C3, and C4, then you choose I equal to 1, so I choose C1. Then from C2, C3, and C4, there are 3 tangent points. Okay? Each two will be tangent, so they are mutually tangent. So there are these 3 points. So you draw a dotted circle and call it A1. Okay. Similarly, you will be able to get, you take C2, fix C2, then C3, C1, and C4. C3, C1, and C4. There is another dotted circle here. Okay. So there will be 4. So you have A1, A2, A3, and A4. They are called dual circles. And you define gamma I to be the Mobius transformation, which is the inversion about AI.
So is orthogonal to C4?
Yeah, they are all orthogonal. So because they are all tangent, these are all orthogonal. My picture is not good, but you will get exactly similar kind of 4 tangent circles. They are dual to the original C1, C2, C3, and C4. They are just the original 4 circles. You draw their dual circles: A1, A2, A3, A4, and then let gamma I be the inversion about AI. So what does gamma I do? It just takes interior of AI outside and outside to inside. Okay, and gamma I is a Mobius transformation. So you look at the group gamma, which is generated by gamma I equal to 1, 2, 3, 4. And this picture is really an orbit of gamma I, because what you do is, say for example, I had original these three circles. So if I take C, if I take if I take A4, which is obtained by not looking at C4 but just other three. So in A4, if you do the inversion of C4, I'll get then under this inversion, C1 will go to itself, A4 will go, no. So under this inversion, this outside part of C1 will go to the inner part of C1, outer part of A3 will go to inner part of A3. There will just be reflection around this dotted circle. So the C1 will be preserved as a set, C2 will be preserved as a set, C3 will be preserved as a set, and these maps take care of tangency quite well. So therefore, the outer tangent circle will actually go to the smaller circle inside. So the inner circle is really the inversion about A4 of this outer C4, that will be this circle. Like that, this one can be obtained by another inversion by looking at multiple application of gamma. So what you have is that P, if you call this a packing P, which is infinite packing, P is equal to gamma orbit of Ci, which is a union of I equal to 1, 2, 4. So P is a finite union of, so gamma admits finitely many orbits on P. Okay, so this is one example of such a packing. Another example you can obtain is Schottky dance. Huh? What is it? Spelling is wrong, right? SCHO. Another T. Yeah. Yeah, the Schottky dance. So what you do is that you take
So the example one, the gamma is some familiar group.
What is it?
So example one, the gamma is some familiar group.
It's called Apollonian group. Any such two packings are isomorphic under some Mobius transformation. So any two gammas are isomorphic to each other. So it's called Apollonian group. No, this is a non-lattice group. Okay. In fact, it will turn out when I define limit set that limit set of gamma is really just this. It's not just a union, but if you take the limit and everything you get there. It's a closure of this P. That's the limit set of gamma, so it's not that. I will talk about it. Okay, so another Schottky group is you choose finitely many disjoint pairs of disks inside C, and then the map you consider map gamma 1. So gamma 1 takes outside of Ci to gamma I takes outside of Ci to inside, not Ci, Di. So inside of Di and yeah, so that is gamma 1 and gamma 2. I mean Di prime. Okay, so this is Di prime, D2, D2 prime. They are all in the complex plane, and you choose a Mobius transformation. There exists a Mobius transformation, gamma I, which takes D1 to D1 prime, but it takes interior to exterior, and exterior to D. So it's the same thing with D2. And you look at the group generated gamma, generated by gamma I equal to 1, 2. It doesn't have to be 2, you can take finitely many. Okay? You can do finitely many pairs, D1, D2, and so on. And you look at the group generated by that. And you look at the orbit of gamma under Di and Di prime. Okay. In this case, I equal to 1 and 2, call it P. So what will happen is that when I apply gamma 1 to the whole set, then what gamma 1 does is that it takes the interior of this to the exterior and exterior of this to the interior. So therefore you will have a copy of gamma 1 d1, gamma 1 d2, gamma 1 d3 inside here, and then same thing you look at gamma 1 inverse, that will take these three, copy of these three inside here, and it will keep happening, and each time when you apply more and more, it will go deeper and deeper inside. Okay? So everywhere you will have a picture like this, and then the next level, everything will go inside the previous ones. So it will go deeper and deeper. In this case, all the interiors are not disjoint, but again the circles are becoming smaller and smaller. So this becomes a P is locally finite. And so gamma acts on this, and there are only finitely many orbits here. So again, it is a question. Again, it's a packing where the symmetry group of this packing is locally. Has finitely many orbits, and this packing is locally finite. In fact, as soon as P is locally finite, it forces gamma to be a discrete group, because if it's not a discrete group, you will have a sequence of circles converging somewhere, because you can take that limit and cause problems. So it is forced that gamma is automatically discrete because of local finiteness of P. Okay. So now I want to estimate how many of the circles are there in some region E I draw. Then I want to know that given some number T, how many circles of radius bigger than 1 over T, but T is large, so how many circles are circles of radius bigger than 1 over T, which intersect this region. Okay? So that's the kind of question I'm going to ask. And I want to estimate that. There is one more very beautiful packing of this kind. That's called Sierpinski's carpet, and that corresponds to hyperbolic manifolds with boundary and finite volume. But I will not talk about it in a moment. But I will go further. Okay. So now, before I go further, I want to look at so now G equal to P SL2C action on C hat extends to the hyperbolic plane model H3 equal to Z comma T with C cross positive numbers with hyperbolic metric. So it's exactly like we have the upper half space model. Here you have R, and you have R plus, R positive here. You have upper half space, and you have hyperbolic metric here. So in this case, you start with complex number C here and extend the hyperbolic metric to the upper half space in the same manner. And interestingly, that PSL2C action by fractional linear transformations on C extends to this. So the action C extends to this with hyperbolic metric, reserving the action such that the action reserves the hyperbolic metric. And in fact, this acts transitively. discrete by isometries. So this action really extends the action which I already given to you before on C. Okay. So this is just a comment, and that therefore gamma also acts on H3, and he forms a quotient. So you consider, so gamma acts on H3, and we consider the quotient H3 mod gamma, and I need to define some quantities associated to this in order to study my discrete B. So somehow I want to understand this counting in terms of some dynamics on this space. So before I go further, let me just define some abstract stuff in this situation. So you define a number delta gamma is equal to infimum of the following numbers as positive, such that you do the sum. So you fix some x and y in H3, just pick some 2 points, and look at gamma orbit of y. There are lots of infinitely many points, and you consider the sum gamma in gamma e to the negative s times distance between x and gamma y. Okay. So if I consider a sum like this, it's a countable sum. So if s is very, very large, then this will become, these numbers are becoming large when you have bigger and bigger gamma, because gamma is a discrete group, so the orbit is discrete. So it spreads around, the distance between fixed x and gamma y, little gamma y becomes large. So this will converge for large s, and you look for the smallest s for which, you look for all possible s where it converges, and you take infimum of that, you call it delta gamma. And there is a nice observation of Suleiman. So there are 2 papers, one in 79 in IHGS, and later, so what I am saying, most of the time it will be from this paper, but later he had another paper, 84 and hectare, where he talks of other things. But in this paper, he proves that if gamma is not virtually abelian, that means it does not have a finite abelian, a finite subgroup of, sorry, it doesn't have finite index abelian subgroup, then delta gamma is positive, and this is called the critical exponent of gamma, and this is called a Poincare series. So now, critical exponent is always positive, and this exponent is going to play an important role in our counting. So this is going to play a critical role in our game, and just observation that if delta gamma is always less than or equal to 2. Okay, so I am going to assume that it is virtually non-abelian. Okay, if it's virtually abelian, it's cyclic, and no, it's virtually abelian. The whole thing is not interesting and much simpler, but we are going to assume it's virtually abelian. Not virtually abelian. So I have this situation, delta gamma positive. It's always between 0 and 2, which is equal to dimension of boundary of H3, which is C hat, dimension of C hat, which is 2. Okay. And if, then here you have delta gamma equal to 2, if only if gamma is a lattice in G, or H3 on gamma admits the Euclidean volume of this, not Euclidean, the hyperbolic volume of this is finite. That is, if delta gamma 2, you can only that. Okay. And there are some facts which I need to use. Is that again, this is by Suleiman. Most of the result, if I talk about this this kind of groups, it's due to Sullivan and Peterson and Sullivan. So,
the gamma is always flat together.
in this, at the moment, not. This much is. So, what it says is that for every x in H3, so this is a result of Peterson and Sullivan, that for every x in H3, there exists a finite measure through x on boundary of H3, which is C hat, which is like a sphere, right? Such that it has the following properties. Gamma applied to mu x is mu of gamma x. Okay? So it's a measure associated to another point gamma x in the space for all gamma and gamma. So that's called invariance. Gamma invariance in this sense. Okay? The measures are not gamma invariance, but the whole collection is gamma equivariant in appropriate sense. And second thing, mu x and mu y are mutually are absolutely continuous with respect to each other. And if I want to compute the mu y by the mu x, then you can write down by some formula which is looks like e to the negative delta gamma times beta at the point. So these two are measures on the boundary of on C hat. So if it's regular Nicodemus derivative at the point psi in C hat, which is on the boundary, it's some function where beta psi by x is a called Huysman function, and I will not define it. I mean, it's easy to define, but what it means is that I have this x and I have this y, then and this is my psi here. When you look at the holosphere passing from psi here, and you look at the holosphere passing from y and psi. So holosphere base at psi. So look at the sphere base at psi passing from x, and look at the sphere base at psi passing from y, and you look at any geodesic going through psi, then you look at this distance. And that distance is constant everywhere, and this is the sign distance. Okay. So in this case, if x turns out to be the inside of it, this would be positive, and otherwise it will be negative. Okay, so that's the sign distance between x and y base at psi. That's a Huysman function. So its derivative is Huysman function times delta gamma. So you say that this is conformal density of, so it's called delta gamma conformal density. Okay, so where delta gamma is this one. So Peterson and Sullivan said that you have such a collection of density mu x on boundary of Hn. Okay, and then we are going to make use of this density to describe further.
You said derivative of the Huysman function.
What is it?
You said some derivative of the Huysman function.
The Ergodic derivative of y with respect to x.
Is some derivative of Huysman function?
It's not derivative of this one. This derivative is e to the negative delta gamma times this value of this one.
That beta psi.
Huh? What's the definition of beta psi? You look at any, this is by definition formally, it's a limit t going to infinity distance between y and psi t minus distance between x and psi t, where psi t is any geodesic pointing to psi. Okay. So if I have a point psi here, you look at any geodesic that entering psi, and you look at this x, you look at this y, and you look at this distance, hyperbolic distance between x and this, hyperbolic distance between y and this, and look at the difference in appropriate order, and you take the limit as you go. This number is independent of choice of this. Okay, so now I will define a particular measure, omega gamma, on C or C hat, okay, measure on C hat. And how we define this measure? So you fix some point O in H3. Okay, so this measure will initially depend on, the definition will depend on O, but in the end it will not.
Just to remark is that if gamma is a lattice, then delta gamma is 2.
If gamma is a lattice, delta gamma is 2. In which case this is more or less like usual Lebesgue density. Okay. But if it's the sphere model, this, if you take this point O, this point x, then it is the, so if given any x, you look at the stabilizer of x, and this measure is invariant in the distance. And later.
So almost true that if delta gamma is 2, then gamma
Yes.
is true.
Yeah. Okay, so what I was saying? Yeah, so I define measures. Yeah, omega gamma of psi. So let psi be a CC infinity of C, some compactly supported function of C. So I want to integrate psi with respect to omega gamma. So in the notation I am writing this. And this, by definition, is integral over C of certain quantity, which is psi of Z times e to the delta gamma of omega psi. Don't worry about some numbers, x and z comma 1. So let me just say I fix O, so O comma z. So nu naught z is a measure on C. Yeah? Nu naught z is a measure on C or C hat, and it's okay to take C hat also. In which case I only need to take continuous functions on C hat, but then it's also okay. I mean just continuous functions on C hat. So then you define it. Okay. This is a measure on C hat with respect to O, and you multiply by some number. This is O and this is Z comma 1. That means given any Z, you look at the other coordinate, you look at 1. And x. And given any Z here, you look at this Huysman function, you multiply by its number, but you get some measure. So for example, so this definition is independent of choice of O because of these properties. Okay, this property. This is exactly how it is done, so that it becomes independent of the choice of O. And
The integrand is minus delta.
minus delta here. No, yeah, but here you don't need minus. You put it positive so that it cancels out. Then when you make the changes, things cancel. Okay, and it's independent of choice of O. So if you put O equal to 0, 1, that is, if I choose my O to be, this was my O. But if I choose my O to be this one, then it's much simpler form. Omega gamma psi is equal to integration over C hat of psi Z times 1 plus mod C square to the power delta gamma times C mu naught of. So in this case it's simpler. Description is simpler. Okay, you can just compute explicitly this number, that's all. Okay, so what is the theorem which I want to say? So theorem, this is the all what I am saying is joint work with EO. The theorem says that if P is locally finite with finitely many gamma orbits, and I need to put one more condition. I'll put one more condition. If gamma is geometrically finite and if either delta gamma is strictly bigger than 1, or if delta gamma is less than or equal to 1 and P does not contain infinite bouquet of tangent circles, in fact double infinite bouquet of tangent circles. So I will explain these conditions shortly. Namely, my configuration should be such that I don't have the following situation. I should not have this kind of configuration inside my this is I don't want this. Okay. If my delta gamma is less than or equal to 1, in that case I don't want this. It causes some problem. But if it is not less than 1, strictly bigger, less than or equal to 1, but if it's strictly bigger than 1, I don't care. It can be there. If this happens, then
Local finiteness
is local finiteness.
does not.
No, because it doesn't converge. It converges to a point. You see, local finiteness means you have lots of circles with infinitely many circles with radius bounded below inside a compact region. Inside a compact region. Okay? You shouldn't have something like this. They all converge to a circle of strictly positive radius. That is not allowed. That's locally finite. But it can go to 0. It's not a problem. There it's not. There is no circle there. The point is not a circle. Okay, so this configuration is the only configuration that's not allowed. In P, if it's there, it's you have to argue different things. Okay, so then anti PE is when limit P going to infinity, anti PE divided by P to the power delta gamma is some constant which only depends on P in gamma and times omega gamma. So it really converges. So the number of points here is of the order of T to the power delta gamma, and the relation with E is some constant which only depends on P times omega gamma. Okay, and what is the condition on E? You want that boundary of, so E belongs to contained in C, and boundary of E has 0 measure, U0 of boundary of E equal to 0. Look at this condition, has only, doesn't matter what O I write, because all these measures are mutually, all these measures are equivalent with respect to each other. So anyone, with respect to any one of them, the boundary of E should have measure 0. It means if I take E and if I take interior of E, right? Closure minus interior should have measure 0. So essentially, yeah, so that condition I need some flexibility here. If that is so, then it converges to this number, and description of CT will come later. He needs more notation to describe. So this is a very interesting number, but I also need to tell you what is geometrically finite. Geometrically finite says, statement says that you start with some configuration of locally finite configuration of circles in C. Start with the locally finite configuration configuration of circles in C, and suppose and consider gamma to be the group of Mobius transformation which preserves this configuration. That's some discrete group gamma. But the most important condition is that gamma has only finitely many orbits on P. Okay, so gamma is big so that it has finitely many orbits on P. Furthermore, maybe your configuration tells you somehow that gamma is geometrically finite. I will explain what it means.
So if it is not geometrically finite,
if it is not geometrically finite, I need to say something more. Okay? Yeah, you need something about
so
some
that's
condition.
your hypothesis.
This is my hypothesis. This is my hypothesis. Okay? These are all given. If. Okay? These are all given. Plus, I say that if the delta gamma is always less than or equal to 2 and strictly positive, if it is bigger than 1, I have no problem. But if it's less than or equal to 1, then I don't want a configuration like this in my space. There is some reason for that. One can understand this also, but okay, yeah, I don't want such a picture inside my P. If that happens, then you can compute, and it's a rate of t to the power delta gamma, and the answer is this constant times this measure E, and this measures this or whichever, this one. That's it. So, what more I want to say? What is geometrically finite? I will not say anything more revealing, but in this particular case, for SL2C, geometrically finite is equivalent to finite-sided fundamental domain. So in both the cases I said about Apollonian circle packing and Schottky dance, one can easily describe, obtain finite-sided fundamental domain. And this is also equal to saying, I think, finitely, but it won't help much, finitely generated and finitely presented. Okay, but this is not really, this is not for us. There are much more geometric definitions of geometrically finite which is more appropriate for generalization of HM, but I just don't want to introduce more and more things. So, in Schottky dance, what you can do is that you have this original disk D1, D2, D1, D1 prime, D2, D2 prime, maybe another disjoint D3, D3 prime. Then you take the original big disks and take its, now the next game. So one more thing I need to tell you. Now how to approach this problem. Given any C in circle, in complex plane, you associate with this. In the complex plane you take some circle, then associate with this the half sphere. You call it, given any C here, you consider half sphere C hat. Above C, okay, above this circle. And so what you do is that you have this finitely many disks, so you just take the half spheres above these disks and remove all that part, the half sphere along with the interior. Remove all of that from your domain from H3, then the rest of the region is actually works as fundamental domain for Schottky dance, in which case finite-sidedness comes out of. So these boundaries are totally geodesic subspaces inside this hyperbolic space because it's all these lines are orthogonal to the surface. So this is totally geodesic. Huh? Formal geometry. Okay. So I want to finish very quickly. All right. So in order not to take more time, how this result relates with dynamics. So I will just take the result in dynamics. So I will assume P is equal to gamma orbit of a single circle C0 because there are only finitely many orbits, so I just look at one of them. And for C0, this base circle, I look at this and I look at H. Yeah, that's it. I look at this surface and let C tilde, C0 tilde equal to unit normal bundle over C hat. That means each of this point we look at the unit vector which is normal to each point of the sphere and going outside, and also you can choose vectors going inside. So there are two components of this unit normal bundle, and you look at H. Yeah, that's it. And look at H equal to those G in ESL2C, so that G preserves this this circle, this sphere. So that means the action of G will preserve this, okay, this C hat, and this is isomorphic to ESL2C, and maybe the identity component of that is isomorphic to ESL2C, and there is one more element H which is just reflection about C hat. So that is the group H I am looking at. And C0 tilde admits, so the C0 tilde is inside P1 of Hn. So this admits the big, H invariant measure. And therefore on C0 tilde modulo H intersection gamma. So this measure let me just write for short this measure is on C0 tilde. So I go modulo H intersection gamma. Then on this I have the measure the image of this Lebesgue measures, and what I do is that I consider the integration of any function f, so that f belongs to CC H3, not H3 mod gamma, maybe T1 H3 mod gamma, unit tangent to H3 mod gamma. You consider this function f, and you consider a geodesic flow GT on this space, and you apply to some x. You see the big x in C0 hat mod H intersection gamma. So you flow this surface by geodesic flow for time t. So it will become some kind of lens around this C hat, some kind of lens at a time. All points at distance t from C hat. So it will be on both sides, it will go distance t from C hat. You integrate your function on that, and you transfer this measure I have on this thing, and you integrate this. So in general, if t is not a lattice, then this will go to 0. But if you multiply by e to the power 2 minus delta gamma, so if delta gamma is less than 2, then it is positive times t. You take limit t going to infinity, then you can show that this is equal to d times some measure, which is called Berger-Rogna measure of this function f, and this has very interesting meaning. So you have to prove this result in dynamics, use certain counting technology of Wood-Mexana, and you get some other ideas. I'll stop. Yeah, even if it's not geometrically finite, I need to assume two things. There is something called Bowen-Margulis Sullivan measure on G mod gamma. Then that measure should be finite. That's one condition. And basically you need that condition. If you have that condition, you can skip for this. Or basically you need that condition plus I need another condition that in some sense there is some measure called Peterson-Sullivan measure on this. The Peterson-Sullivan measure on this should be finite. Two conditions are needed. And these conditions, having no bouquet ensures in geometrically finite case that Peterson-Sullivan measure of this is finite because that appears in this concept.
And if not, I mean,
if everything that they defined are finite, then this is good.
no, but if not, can you imagine there might be some strength group where there's some fluctuation?
Yeah, about that I have no understanding. Because I use mixing of geodesic flow for Bowen-Margulis measure. If I don't have it, I don't know how to process.
Paper on the archive?
No, this is published. It's in Instrunex 2012. Yeah, this result is it's just posted on James. It's Journal of
It comes straight focus. You need to get this.